Greetings. My name is Charles Takalana, and I am an astronomer based at the South African Astronomical Observatory in South Africa. I am also the Deputy Director at the Office of Astronomy for Development, which looks at how we can use astronomy to address challenges that society face. First, I'd like to thank the organizers of the hackathon under the Research and Innovation Working Group. Uh, and basically, this hackathon was looking at how we can forecast informal urban expansion and flood risk. And my solution basically looked at how we can assess urban growth, flood hazards and risks, and demonstrate the use of open satellite data, machine learning, and I then also translated that into creating a dashboard that can be used for this. I'm going to share my screen, so let's see that. Yeah. So why does this matter? Africa, urban population is always is rapidly expanding. The population, continues to grow, and with this, due to the lack of resources available, it is difficult, for people to be able, to afford proper housing, and therefore there's a growth of informal settlement. And most of these happen to be in very high risk flood prone zones. And flood disasters are therefore increasing as well due to the effects of climate change. And it's becoming increasingly important for policymakers to be able to make evidence-based decisions, based on spatial insight, so that they can act in a way that can save communities. So what I've built here is an end-to-end pipeline. And it's a fully open, it's built fully in the Python language, and it directly ingests data from Sentinel to imaging data, which is available through the Digital Earth Africa platform. And and we use the Digital Earth Africa platform, which is a cloud-based platform, and we sort of and one that is also open source. Being able to have this data available to us so that we can use it to find solutions like these. What the pipeline does is that it looks at change detection in terms of urban growth. We use the normalized difference build-up index, where we detect where new settlements have appeared in satellite imagery over time, and where the older ones maybe have been lost or damaged through some process or the other. And this shows how urban expansion this shows us, the urban expansion patterns in sort of, as a function of time. So what I also do, I also look at, forecasting expansion using machine learning models. So in this case, I use random forest and logistic regression on some historical spectral data. And these models then predict which areas are most likely to experience urban growth over, a period of 1 to 3 years that I was looking at. And we present both, a conservative and and more permissive outlook. Also look at flood detection in terms of and as well as hazard mapping, and use water indices to compare pre-flood and post-flood conditions, and also look at risk classification. And then I put all of this information all together thereafter into a dashboard. So what are the areas that I used or studied in particular? So I tested the work that the methods that I used for this work, on the township of Khayelitsha in South Africa. I looked at a number of areas in Durban, including Quarry Road West, Molweni Village, Mosley Park, which have over the past years, been reported to have had some sort of floods. Also looked at other parts of the African continent in Nairobi, Lagos, and in Mozambique. Um, and basically these cities, have already have some sort of high risk and sort of informal settlements as well. And they capture a number of geographies. This include coastal cities, inland floodplains, and also wetlands that are encroaching, and also some wetland encroaching settlements. And this geographic spread demonstrates that the pipeline can be used for diverse African context. So starting with the change detection, which was done using the normalized difference build-up index, which is a satellite index, that highlights the build-up material. So it will basically detect things like, concrete and rooftops, and comparing the baseline, composites versus the recent composites, and we identified where new buildings appear and where build-up, disappeared, where there was a building before and there was all of a sudden there isn't, a building. I show in the images here two cases, which is one of Durban Quarry Road, and that's the one that's on my left, and then I also, which has revealed 13% of growth in 1 year, and on the right I've got Khayelitsha, which shows or which I picked up 7% of growth in the same period of a year as well. I also look at, for the change detection, also looked at other statistics, using the pixel count, and this included both looking at the growth, which is the new build-up, and the loss, including buildings that are no longer there. And the change detection highlights, some rapid expansion trends, and these can be used by policymakers to sort of make decision, or sort of assess where new buildings are coming up, and also identify those that are also informal settlements and where action might need to be taken in order to avoid disasters. And then in terms of forecast expansion, I then trained a machine learning model. So the models that I use were random forest and logistic regression. And the difference between the two is that the random forest, it's good for feature analysis, but it's also very computationally expensive when it takes more time to run. And then the logistic regression, does not really, give good feature analysis, but it is more computationally cheaper or takes less time to run. And I use various spectral features, including the normalized difference vegetation index, looking at at green vegetation, the normalized difference buildup, looking for roof and concrete signals. And then I also use the normalized difference water index, which highlights open water and wetness, as well as the modified normalized difference water index as well, which then helps isolate water in urban areas, for example. Right. So these models, learn from past growth pixels, and then, predict, the future expansion. And so we produce, for example, for this work, maps and then threshold them into 1 year, which is much stricter and much looser 3 year forecast. So what you have here, for example, for Kailicha, I've got the 1 year expansion forecast at the top, and I got the 3 year expansion forecast at the bottom. And these sort of things then allow for 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 planning ahead, where and also where to expect future settlement pressure and how to mitigate, any sort of risk. And I then moved on, from looking at the forecasting, of growth of informal settlements or some form of settlements, and then looked at the flood detection part of the task. So, the flood detection compares the baseline or pre-flood window with the event, which is then, the event is during the flood. Um, and and the normalized difference water index and the modified NDWI, highlights the water, and the changes between the two reveal, the newly flooded areas. And so in this maps, what we show is how water sensitive indices change between the baseline and the event, which is the flood. The blue areas, for example, would indicate, stable water, while the sort of red or more sort of purplish parts, highlight new or increased wetness and therefore, signals, some flooding. So this is effective in urban areas, where shadows or dark roofs, might, otherwise confuse the signal. But, for example, this was not the case here. We're not looking at a more urban area. This was sort of a more coastal area for this Beira example. Then we create the hazard baseline, for essential risk planning. And basically, the image that you see here is the cleaned and binary layer of new flooded water pixels. So what you see is basically just the new water in the blue. And it only isolates new water that appeared during, some flood window, but was absent in the baseline. So for this case of Bera, you can see, you can see the flood waters extending into some blocks, and each, and which then matches, some reported flood event, So together, with all of these layers that we have in terms of the flood detection, they, both the signal strength and and also the actionable footprint, which is now, the flood extent that we see with this image. I also looked at the mapping, vulnerability, so identifying, vulnerable areas, and in this case, I looked at the Mosley Park scenario, and so we've split this into, into 3 layers plus a combined index. So we looked at hazard, the hazard, which is looking at the flood frequency, which shows us how often an area floods across multiple events. So the dark blue, would mean that it's repeatedly flooded zones, for example, and the exposure then looks at the buildup intensity, which uses the normalized difference buildup index to identify where buildings, and settlements are concentrated. So basically, the stronger yellow orange, means a more denser buildup. Also proximity, you also measure the closeness to water bodies and settlements near, whether it's near rivers, near wetlands or coastline. And those that are near, these sort of areas are then, scored at higher risk. And then, of course, we then have the composite of the vulnerability index, which is the combination of the weighted, importance, or basically, looking at, it takes into account 35% of the hazard, 35% of the exposure, and 15% of the proximity, and then this gives us, this holistic hotspot map that we have here at the end. Um, in terms in terms of now the risk classification, it then fuses the forecast expansion with the flood hazard maps, and the new growth in the frequency of flooded areas would mean that these are more high risk areas, and any growth nearby would mean that these are medium risk, and growth in upland or unsafe zones, or rather, or in growth in higher land or in safe zones would then mean that these are lower risk. So we looked at this example, which was Khayelitsha, and we see that the informal settlement is expanding. There's that specifically the informal settlement of a En- Enka Enkanini is expanding right along, for example, a wetland and flood prone zone. And so this risk map shows, some clusters of high risk growth where the urban expansion overlaps some of the recurring floods. So in this slide, we now have the histogram, from the data for the risk classification, and it illustrates the proportion of new settlement growth, into low, medium, and high risk classes. And we can see that, for example, in this histogram, the low risk is dominating, but there is eventually, a potential swing, if new settlements start, for example, coming up in more high risk zones. This type of spatial intelligence, is something that will be needed, if you want to make, good policy action, and to guide, the safe expansion corridors, and to improve drainage or support the community in terms of relocation, and where, in some cases that may be absolutely necessary as well, when for example, that the flood seasons are close. So basically, the heart of the solution, as I mentioned in the beginning, is this dashboard that I prepared, and I just named it the Urban Flood and Growth Dashboard. So it pulls together, all the analytical products, from the Python pipeline that I worked on, and it puts it into this easy to use interface where policymakers and emergency workers and planners, for example, can come and sort of have a look and play around with, and also be able, to identify risk areas and make decisions. And the dashboard makes all analysis, accessible even to a non-technical user, because it includes a summary table, which I showed in the beginning. It also is sectioned into different cities. So say, for example, if it is, if the database grows, you can just populate it with different places, or with coordinates, and then you would be able to sort of find the risk or the location for that particular area. And of course, with each and every image, it sort of gives an explanation of what the image is about. And then, of course, to ensure, or or to verify, it also includes the true color satellite image as well. And then these then are then followed by those important sets that looks at the flood maps, such as for example your flood maps, your vulnerability panels, and your classifications. And then all of this brings the data to life for those planners and the emergency services and policymakers. Okay, so policymakers can use, something like this dashboard and, and the various solutions that we propose, to define safe urban growth corridors, to identify and prioritize, high risk settlement, in order to make any form of interventions, to guide any infrastructure investments, and flood defense where they needed most, and to foster community engagement, involve the residents, in co-developing adaptation strategies, yeah, for, that can sort of, make sure that we save lives, when things such as floods, occur. And just in closing, this work, connects satellite intelligence directly, with actionable policy through the dashboard. And our solution directly supports, resilient climate smart urban development. It will also be able to empower emergency services planners and policymakers with some actionable intelligence, and most importantly, it can be used, for any area or any place on the African, continent, or whatever the case is, as I demonstrated, applying, the pipeline in all the different areas that I showed during the presentation. And of course, due to this data being available through the Digital Earth Africa platform, it is freely available, and all of this will be at a low cost. If someone is using the Digital Earth Africa sandbox, for example, to make the analysis like we did here, and moving forward from this, we can move away from not just leaving it as a hackathon solution, but, using its potential, as a continental resource for resilience. So I'd like to thank the organizers of this hackathon one more time. And, I'd like to thank you for your attention.